This is a video for AQA Discrete Mathematics, Binary Operations Section 2.2, Working with Groups. Well, here's a finite set EAB, and we have on it defined an operation delta given by the results in the Cayley table. The question then is to decide whether this is a group or not. Of course, if it's going to be a group, it needs to satisfy each of the group axioms. So firstly, we need to check, is it closed? Well, yes, we can see that for all elements, then the result of combining them is one of E, A, or B. So yes, it's closed. Next one to decide is there an identity element? And clearly then we can see that E is an identity, so yes, E is the identity. And then, do the elements have inverses? Well, E is bound to be its own inverse because E combined with E is E. What about A and B? Well, we can see that they are both self-inverse because A is equal to E and B is equal to E. So each of the elements is self-inverse, so yes. And then what about associativity? Well, we can check that. Well, let's check, for example, A combined with B. Well, first of all, if we do that, B of course is E, so that gives us AE, which is just equal to A. And if we do it in the opposite order, A combined with B and then B, well, AB, we can see from the table, is B. So combining them in this order gives an answer E, and therefore associativity fails. We can say therefore that this is not a group. So whereas we had the first three of the axioms were fine, closed, identity and inverse, all satisfied, however the associativity is not. Now it's always going to be the case that for a group then the Cayley table would produce a what's called a Latin square, so it would have each of the elements in each row and column, and we can see this one doesn't. For example, in the third row there we've got the elements B, B and E, so A doesn't appear there, and therefore we could see directly from the Cayley table that it's not going to work. However, what you should do if you're asked to do this is to go through each of the axioms and check each of them in turn. Let's now consider a second example. This time we're going to be looking at the integers under addition. This sometimes you'll see written as Z plus, where Z is just the integers and the operation plus. Now, the first thing to note is of course that Z has got an infinite number of elements, and therefore we can't actually check by using a Cayley table. We can't literally write down an infinite number of different operations, and so we can't use that in the same way as we can with a finite set to check whether this is a group or not. However, that doesn't stop us deciding whether it's a group, because we can use our knowledge of integers and how they combine to see whether each of the group axioms is satisfied or not. So again, taking them one at a time, is the set closed? Well, we can say that for all values A and B that are elements of the integers, then A plus B is also an element of Z, so yes, it is closed. Is it associative? Well, this is something that you're very familiar with. A plus B plus C is equal to A plus b plus c with the bracket written in a different position. So yes, it's true for all values of a, b and c that are in Z, and therefore we can say it is associative. The next axiom is to check whether there is a unique identity element, and we know that for all elements that are integers, then if we add 0, then it's the same whether we do 0 plus a or a plus 0, we get a, and therefore yes, then the identity element is 0. And finally, does every element have an inverse? Well, again, a plus negative a is the same as negative a plus a is equal to 0 for all values that are integers. So yes, it does have an inverse. So we've got all 4 axioms are satisfied, and therefore it must be a group. Second example of an infinite set, let's look at Z under multiplication. In other words, we've got the integers under normal multiplication. Again, going through, is it closed? Well, yes, a multiplied by b is an element of Z, so if we multiply 2 integers together, we get an integer. Is it associative? Well, yes. No need to write it down, we know it's associative. And is there an identity? Well, for multiplication, 1 is the identity because a multiplied by 1 will be equal to 1 multiplied by a for all a that are in the integers. But then we come to the idea of an inverse. We would need a multiplied by something equal to 1. And of course there's no integer, for example 2, there's no integer multiplying by 2 to give us 1. We would need fractions. So we need to go into the rational numbers. And so therefore we can say that there is no inverse for any value of a other than 1 itself. So because it doesn't satisfy all of those axioms, then Z multiplying is not a group. Some definitions that you need to know then about groups. Firstly, the idea of the order of a group. And the order of a group is simply the number of elements that it contains. So we know that these are both groups, and we can ask what's the order, and of course the order of the first one has got 4 elements, so this is order 4. The integers under addition, we've just decided, has got an infinite number of elements, so we'd say that this is infinite order. So the order of the group is simply the number of elements that it contains. The order of an element, however, is the smallest n such that we have a to the n is equal to e. Now, e is the identity element, and this notation here is used for multiple use of the operation. So for example, if we have an operation star, we would say that a to the power 4 is a star a star a star a. So it's just 4 times we've got the element itself. Well, let's look at this Cayley table then for multiplication using complex numbers and decide on the order of each of the elements. So looking first of all at -1, we can see that -1 combined with -1 is 1. And therefore we can say that that is order 2. I combined with I, we can see on the table that we've got I and I, that's -1. So I combined with I is -1. But if we then take -1 combined with I, that's equal to -I, or in other words I can write that as I multiplied by I multiplied by I is equal to negative I, and then taking negative I combined with I, we finally get to 1. So we can say that I to the power 4 is equal to 1, and therefore I is equal to, or has an order 4. And you can check to show that negative I is also order 4, so that negative I to the power 4 is equal to 1. So the order of the element is the smallest value of n such that a to the power n is equal to e. If there's no value of n, then we say that the element is of infinite order. So let's look at modular arithmetic now. Remember that with modular arithmetic, it's the same. We're looking at doing the arithmetic and then dividing through by 5 to get the remainder. So we're asked what is the order of the element 3. Well, 3 squared is 3 plus 3, so that's 6, which is remainder 1 when we divide by 5. So 3 squared is equal to 1. Therefore 3 cubed will be 1 plus 3, which is 4. And 3 to the power 4 will be 4 plus 3, or 3 plus 4, which is 7, which is 2. And then finally 3 to the power 5 will be equal to 2 plus 3, which is 5, which is remainder 0. And of course 0 is the identity element for modular arithmetic under addition. So we can see that 3 to the power 5 is the first time we get to e, and therefore we can say that 3 is of order 5. That's the end of this particular video. In the next one we'll be considering the idea of abelian groups.